Hi everyone, I'm Jitesh Jain and I'll be presenting our paper SeMask, Semantically Masked Transformers for Semantic Segmentation. This work was done in collaboration with the Pixar AI Research, University of Oregon, UIUC, and Georgia Institute of Technology. To give a brief overview of the contents that I'll be covering, I'll be first giving an introduction to the semantic segmentation task and the status quo methods. Then I'll be diving deep into our proposed SeMask method and sharing the results for the same. So, the task for semantic segmentation tackles the issue of pixel level classification, where we want to assign a label to each pixel present in the image, and the pipeline goes something like this, where we input an image and there's a model in between, a semantic segmentation model, and it outputs the pixel wise category map as the result. So, existing vision transformer frameworks approach the problem in either of the two ways, where first they propose their own backbone, which is pre-trained on ImageNet, and use any existing standard decoder to transfer it to the semantic segmentation task to show the effectiveness of the backbone. A second set of works usually design a new encoder as well as decoder, and they usually train the encoder on the ImageNet before transferring it to the semantic segmentation task. So, in conclusion, the pre-trained backbones are fine-tuned as encoder during the semantic segmentation task. So, in SeMask, we claim that pre-trained encoders do not harness the semantic context during the fine-tuning due to the relatively smaller size of the dataset as compared to the ImageNet dataset, and also the change in number and nature of semantic classes. For example, the AD20K only has 150 classes, but the ImageNet dataset has 1,000 classes. So there is a drastic change in the number as well as the nature of the semantic classes from the classification task to the semantic segmentation task. So our SeMask framework incorporates semantic information into the hierarchical vision transformer architectures and augments the global feature information captured by the transformers with a semantic context. As you can see on the diagram on the right, existing works usually use some transformer layer stacked as encoder and use a decoder. But what we do is we incorporate some semantic layers into the encoder architecture and also use a semantic decoder during the decoding stage to first model the semantic prior, and thus we show major improvements on the semantic segmentation performance. So the baseline for a method is SWIN FPN, where SWIN is a very standard hierarchical vision transformer used widely in the vision community. So SWIN FPN uses SWIN transformer as the encoder, and semantic FPN, which is a very simple decoder structure for the decoding stage. So how we go from SWIN FPN to SeMask FPN is each transformer layer in SWIN contains n SWIN blocks and model the image level features. But that's where SeMask comes in. We add NS SeMask block to each layer of the encoder and to model semantic context in the image. And in addition to that, we also use an extra decoder, which is a lightweight semantic decoder, which is just aggregating the output or the semantic prior maps from the SeMask attention block, and then calculating a CE loss on that, so that we are able to model the semantic map in the semantic context well enough. So with the addition of the SeMask attention block, we are able to model semantic context effectively. Now, the architecture of the SeMask attention block is very similar to the standard SWIN attention block, with a very significant change of changing the dimension of the value of the query and the keys which are used to calculate the attention score, or what we call the segmentation score in a SeMask attention block. So the change is in the embedding space, where we project the input to the SeMask attention block to a k space, where k is the number of classes in the data set. So what we are doing here is we are constraining the query and keys to represent a binary map for each category that is present in the image. So we are disentangling the semantic space for each category, and thus we are augmenting the semantic capabilities of the model. So the SeMask attention block takes in the image level features as the output and then outputs the features with semantic context added to those, and also a semantic prior map gives the SeMask attention block a signal from the ground to the semantic map during training. We do not use the semantic prior map during inference. So to show the results, we conduct experiments on 3 widely used datasets: the ADH20K dataset, the Cityscapes dataset, and the CocoStuff 10K dataset. So as you can see in the tables, our SeMask shows impressive improvement as compared to the baseline Sven FPM method with an increase ranging from 0.5 to 3% in the MIU score on each of the dataset. We also analyze the feature representations inside a model where we calculate a pixel-wise similarity for a randomly chosen pixel, which is the pixel inside the crosshair. And as you can see, the post-SeMask features are better looking with better boundaries and richer in pixel similarity than the pre-SeMask features. So that's one of the main reasons why our SeMask shows so much improvement over the baseline methods. And this is a table for pseudo comparisons. So when we worked on the paper, SeMask outperforms all the SOTA architectures from then and shows impressive performance on both AD20K and Cityscapes dataset to achieve new state-of-the-art performance. And yeah, that's it. Thank you.